If not, Nicole came in as I was sleeping.
That's annoying.
Okay, so we are still missing about 10 of us. So maybe I'll wait another 2 minutes. Okay, I think we're close. All right, so this is the end of week 9. So some of you asked me what was the lab this week, and actually, this week is just we don't have lab. It was a makeup week for previous labs, and instead I was going to post a guidance about the lab final, and the lab final next week will be take home, and it will be short answers, not very difficult, but it will be short answers, and you might have to reach for external resource, and it's open book. You can do whatever you want. So basically, it's like an assignment, but it's related to the experiment that we have done in this quarter. So I'm going to post that guideline after this class. So a few other announcements, because we are approaching the end of the quarter, so it's getting very busy. So this week we will have our quiz and the lab report for due, the tomato processing lab report. And some of you emailed me that the cold break and hot break group kind of had the reversed viscosity. Actually, I think the groups, these two groups, they recorded results. They did the experiment properly, and it was just the odd results from the experiment, which is very common. If you do experiment, there's always some result that you can hardly explain. That's a nature of experiment, and I highly encourage you to try your best to interpret the results and try to answer the question why we got all the results. Any reasonable answer, I will give you the full credit. I basically I won't judge how you you know how you interpret that, because with those results, any guess is possible. And tonight we'll post quiz 8 and assignment 5, and also I'll give you the lab final guidance. It will just be a like outline about what we'll what we'll cover in the lab final. There's not much details, okay, and for the next week it will be a very heavy week. So I kind of extended the deadline for all the assignments and the take-home exam to the end of next week. Basically, it will be Sunday at midnight. So a quiz, another the last lab report, the lab report caramelization, the last assignment that will be available today, and the lab final, which will be available next Monday. So all of them will be due by the end of next week. So try, if you need any extension due to like because you have other projects, or something like you can hardly manage. I mean, you can come to me and we can discuss about extending your deadline. If I see it reasonable, reasonable excuse, I will be happy to do that. And our final exam, as I mentioned, initially was scheduled on next Friday, the 7 to 10 p.m., the last time block for final exams. And I know many of you had already had the holiday, the break plan. So I kind of make it more flexible. So it'll be available from Monday night at 5 p.m. and all the way, it'll be available all the way through the Friday night. And the lab final exam will be 3 hours. Okay, and I know that many of you might need to reach to me for asking questions about the the quarter, the content we have covered in the entire quarter, and my office hour might be too short. 15 minutes is probably too short for you. So if you need any help in the next week, just email me and we can block a half an hour or 1 hour to go over those parts that you are still not clear about. So that might help you better prepare your final exam. Any questions?
So do we have lecture next week on Tuesday and Thursday?
Yes, we do.
Okay.
And yeah, there'll be lectures, but one will be, so one topic will be irradiation. The other topic will be more like open, open lecture. I might give you some, I will talk about something trending topics like sustainability, environment. So still I'm planning for that. It's kind of like a flexible lecture, and I won't cover that in the final exam. So, but there will be lectures. The short answer.
Thank you.
Sure.
Oh, yeah. So that means
All right.
you don't want to learn about frozen foods? You don't want to learn about frozen
So our learning objectives today. First, we'll talk about the purpose definition of freezing, and then the freezing point of different. If we have mixed the liquid, would be the freezing point, and also the concept of supercooling. And also we'll do a little bit of calculation about the thermal energy during the freezing. And we'll also talk about the freezing systems. And finally, a little bit about the impact of the quality on the quality. So there are a lot of content to cover, but at the end, you'll see that everything is very similar to other unit operation that we covered. Let's start. So the purpose of freeze actually, I don't want to ask you anymore because it's very similar to what we have discussed last week, right? It's to extend the shelf life and also to preserve the color because the food properties, because those chemical reactions will occur in a much lower rate when we have lower temperature, right? So the purpose of freeze is very similar to the purpose of refrigeration, but the difference is that the freeze actually maybe extend the shelf life a little bit more, but other than that, they are quite similar. So so here's my question. So if we want to freeze a food, we know that the freezing point of water is 0 degrees C. Do you guys think that the water in the foods will be frozen if we apply 0 degrees C to the food?
No.
No? Yes? Do you want to share why you think it's no?
Because the freezing point of everything else would be lower than 0, and so then it would kind of keep distributing heat.
Excellent, Christine. Yes, you're absolutely right. So one of the example is that I guess the rest of the California experienced the crazy storm this year, and probably if you because I lived in Midwest for a long time, and every year at this time we had the salt. We have seen those salt on the road, and those help to melt the ice, the snow. So the reason behind that, as Christine mentioned, everything that we add into water kind of make it harder or more difficult for the freezing to occur. That's the reason that when we add any impurities, we kind of make the crystallization process more difficult because we have impurities kind of to block that crystallization site, right? So because the water, when initially it wants to form a very nice like network structure of crystal. But if we add some gas molecules like sodium chloride, that kind of disrupt the very beautiful crystalline network. So in that case, the freezing becomes more difficult, and we do require much lower temperature to achieve those crystallization. And in this case, it will be more like a co-crystallization, which means the sodium chloride is part of the crystal. So when you look at the chart in the left, you'll see that the x-axis is the sodium chloride concentration, and the y-axis is the temperature. So if we don't have any sodium chloride, the freezing point will be 0 degrees C, right? That's the freezing point that we know. But when we have 10% of sodium chloride, the freezing point will drop to -5 degrees C, around there. And if we keep decreasing, and finally, if we reach somewhere close to 28 degrees C, the freezing point will drop below -20 degrees C. So I think the majority of the US states will not have that low temperature. So if we add those salt, it will definitely help us to melt those ice. But if you live in Minnesota or Wisconsin, that salt might not help anymore, because when the temperature drops to below 30, nothing can help it, right? So that's but you can see it dropped a lot, right? From 0 degrees C to -20 something degrees C by adding the salt. So same thing happens in food, actually, because we know that in food we have a lot of minerals and the salt, right? And the sugar and the proteins, and everything that in the food, they are regarded as gas molecule or impurities in water, because when we think about the freezing process for water, anything other than water molecule will act as a inhibitor for the crystallization process to occur, right? So that's why when we look at our foods in general, poultry products will have 27 degree F. So because my information is coming from different sources, so some of them use degree C, some of them use degree F. So just give you so 0 degree C is about 32 degree F, right? So poultry 27 degree F is about 3 to 4. It's 5 degree F below the freezing point, so which is about 3 degrees C below the freezing point, right? So strawberry is a little bit better, just 1 degree C or 2 degree F below the freezing point. So depending on the food that we deal with, their freezing points are quite different. So this is extremely important when we are developing our freezing system for different types of food, right? Because they have different freezing point. And I'm not exactly sure why is the poultry's freezing point lower than strawberries. Maybe if we calculate the solid concentration, the poultry has higher concentration, but that's just my guess. And if you want to find more information about it, I think there are some resources that you can look into. Actually, there's a, if you have taken chemistry class, physical chemistry actually has a equation to calculate how much the freezing point will drop according to what molecular weight, and what molecular weight is the gas molecule, and what molecular weight, what is the percentage of that gas molecule. So there's an equation to predict that, but it's an empirical equation, not very accurate, especially in food systems when we have a bunch of mixture of different compounds there. Those empirical equations, sometimes they lose some accuracy. So if we want to do experiment, if we want to run a freezing plant to process those frozen foods. We still have to do the experiment and to measure what is the exact freezing point to that. So the calculation can only give us an estimation. Okay, so about supercooling, I'm not sure how many of you guys have seen or have done any simple experiment about supercooling, but it's very fun. I will show you a video later about supercooling. So basically, if we cool down a food from the high temperature from room temperature to freezing, it will go through a stage called supercooling. As you can see that the temperature will drop to below 0 degrees C, probably somewhere around -1 to -2 degrees C. Although it passed the freezing point, I mean, this is water, not any food product. Although it's below the freezing point of water, they still remain as liquid, which is very interesting, right? If you think about the freezing, everything, if you have pure water, everything should freeze at 0 degrees C, but that really depends. Okay, so sometimes even at -1 degree C, it still remains ice. And that is because to initiate the crystallization process, there has to be a trigger. Okay, let me show you a video. So in this, so let me finish this curve first. So there's after the supercooling, and you'll see that the temperature goes back to 0. That's when the crystallization process occur, and that actually release a lot of heat, kind of bring the temperature back, right? So and it takes a while until all the liquid becomes solid, and then you can further drop the temperature down. So there's a kind of back forth of the temperature. Okay, so when we decrease temperature to below the freezing point, and then the crystal nucleation process starts, and then that is below the freezing point. Okay, and then during the crystallization, actually the heat will be released to raise the temperature, okay, to the freezing point. And finally, after all the water is frozen, the temperature can only continue to drop down to below the freezing point. So this is a typical cooling curve of a pure water. Any questions about this curve? Okay, let's watch a video about supercooling. Okay, and after this, you guys can probably do a small experiment at your home. It's very fun. I did it for like 5 times, and I think I semi-succeeded once. It's a very interesting experiment. Let me share the sound. Share sound. Okay.
Freeze almost immediately. Well, here's what you're going to need. Some very pure water. Fiji water has been recommended to me by a friend. And obviously we're going to need a freezer.
Let me see. Oops. Wait. Sure. It's I think there's something wrong with my okay.
So you want to see water freeze almost.
Oops. Sorry guys. I'm having problem with my sound today. Okay. Okay.
So, you want to see water freeze almost immediately? Well, here's what you're going to need. Some very pure water. Fiji water has been recommended to me by a friend. And obviously we're going to need a freezer, some way to cool it down. So I'm going to put this bottle of water in the freezer in the area normally occupied by the ice cube trays, because I think that might be the coldest part of my freezer. I've got 2 bottles just in case one doesn't work. And now we have to wait. There are lots and lots of videos showing this phenomenon on YouTube, but very few that explain how it actually works. Normally a liquid at room temperature, because the water molecules are all flowing past each other, tumbling around each other, and that allows the substance to flow. When something becomes solid, its molecules all more or less lock into place. They still vibrate, but they're not rolling over each other and moving past each other so they can no longer flow. They're solid. Now what we're doing here is supercooling the water. So we're taking it below its temperature, below 0 degrees, where it should become ice. But it's very difficult for that water to make the transition without somewhere for that ice crystal to start growing. So what we need is some kind of nucleation event. If the water is not pure, the impurities in the water naturally act as sites where the crystal can start forming. That's why it's very important that we use very, very pure water. Another way we can cause this nucleation event.
Sorry. So
And now I'm going to a few hours, and we'll come back and try to nucleate this ice forming event. All right, it's taken a few days and multiple attempts, but I think this could finally be it. I might have finally created supercooled water. So let's find out. I'm going to take the water very carefully out of the freezer. And now you can see clearly that the water is still liquid. You can see this air bubble floating around. And now I'm going to bang it on the counter, and we will see if we can get an ice crystal to form. Whoa, look at that. You can see that ice crystal growing right down from the top to the bottom. So there you have it. I was finally able to demonstrate the supercooled water phenomenon. I cooled down the very pure water in my freezer for 2 or 3 hours, and then by banging the water bottle on the counter, I started the formation of an ice crystal at the top of the bottle of water, which quickly grew down to the bottom. Now, performing this experiment was a lot more difficult than I anticipated. I did this at least 8 times with about 5 different bottles of water, and I only managed to catch it on tape once. So it was a real challenge. Things I learned were that you can't leave the water in the freezer too long, otherwise it will freeze up on its own accord. And also you have to be very careful when pulling the water out of the freezer that you don't bump it, because otherwise it will start freezing right away before you have a chance to bang it on the counter. So give it a try and see if you can make it work.
okay, I think my can you guys hear me? Okay, I think there was I got my problem with my my earbud. So let me reshare my screen. Okay, so isn't that cool? So you guys can probably, if you're interested, can repeat that experiment about the supercooling. It's a very fun experiment, especially sometimes we even can pour the water to the counter, and you'll see the ice. When the water comes out from bottle, it's like a liquid, but once it touches the edge of the counter, it becomes solid immediately. So that is because a little bit of agitation is required to initiate the crystallization process, because it is it needs a little bit of heat, a little bit of energy, just a little bit, to trigger the initial process, so that the crystallization can kind of ongoing by itself. So it's very interesting. Well, okay, so let's talk about the thermal energy. So in last class, in the evaporation, we talked about latent heat and the sensible heat, right? So when we are removing the water from a food product, then it will go through a evaporation process, right? So in that process, we're actually converting the liquid water into gas water, and that's kind of that will go through a lot of latent heat input process. So same thing here. In a freezing process, when we are trying to cool down a food product from room temperature to, for example, negative 20 degrees C, we're also going through a latent heat process and the sensible heat process, right? So these two processes are always required for those phase change. I guess you guys are already familiar with this. So just want to give you a few some information about the latent heat and the specific heat. So specific heat is same for the sensible heat. Okay, so it's for the energy required to change to increase or decrease the temperature without a phase change. Okay, so all the foods have very similar specific heat. Okay, although it varies a little bit, but overall it's in the same range. It might depending on how much water is there, right? The water or moisture content, and also it's affected by other food components. And also for the latent heat, quite similar. The spinach a little bit higher, but they are all in a similar range, right? And the freezing point, they vary a little bit, right? Fish much lower, and the spinach and the peas a little bit higher, more closer to the freezing point of water. Okay, so let's do a quick practice about how much energy do we need to remove during the freezing process. Okay, because it's very similar to the evaporation. So I will let you guys try first, and let's check the answer later. So the question is, how much energy will be removed when we are trying to freeze 10 pounds of fish from 60 degree F to 0 degree F? And so the here's the those parameters of the of fish. The first column, you have the specific heat of fish that is in liquid, or it's above the freezing point. And second one, you have the specific heat of fish when it's frozen, right? So because after frozen, we keep dropping the temperature from the freezing point to 0, right? And the third is the latent heat of crystallization of fish. And finally, we have the freezing point. Okay, so I'll give you about 1 minute to calculate, and we'll check the answer together. It's very similar to the evaporation, so I think you guys can just get started. All right, you guys, did you guys finish? Okay, I saw some. So Christine finished. Okay, let's check the answer because if you have questions, we can talk in our office hour. Because I think that it's very straightforward compared to the evaporation, right? So when you think about this problem, we just kind of draw the temperature curve, right? So the first stage, so we have three parts of this of the cooling process, right? First, we need to drop down the temperature from 60 degree F to the freezing point, and during this time, it's sensible heat, right? And then we kind of we multiply the number with the weight and the specific heat. Okay, it's BTU instead of BUT. Okay, so it's typo here. So that's so here we got the first sensible heat when we are dropping the temperature to the freezing point, right? And then we'll go through a freezing stage. Okay, so in which we'll use the latent heat, right? So latent heat is 122 BTU times 10 pounds. And finally, after everything's frozen, it will go through the from sensible heat to the to drop the temperature finally to reach 0 degree F, right? So let me do a quick calculation so to check with you guys. 10, so 0.8 to, so the first part is 256, right? And then the second part is the latent heat, which is 1220. And finally, we have the last part, which is 112. So finally, I think the energy is 1588 BTU. Did you guys get it? Sounds good. Okay, so this is very straightforward compared to the evaporation, right? So it's just different direction, right? Reverse the way. So if you have questions about this part, let me know. Okay, otherwise it should be very straightforward. Okay, so next we'll talk about some freezing equipment. So this part is very interesting because you will find everything is so similar to what we have talked about before. We're just replacing very small parts of that to change the function, but the design is so similar. It's kind of following the same the thought process. I think the designers, they all have the same mindset of that, those engineering mindset. So the freezing equipment, like we discussed in the refrigeration last class, it has two categories. The first one is mechanical freezer, in which means we have evaporator, compressor, condenser. So it's pretty much like a home style refrigerant system. And the second, we have a cryogenic system, which we use liquid nitrogen or liquid carbon dioxide to kind of contact with the food product directly, so that the food will be cooled down immediately. So this is because it's hard to get liquid nitrogen or liquid carbon dioxide, so it's more commonly used in the food industry for the rapid cooling process, right? So we'll start with mechanical cooling. So the most common one is the air freezing, right? So basically, it's everyone. I think all of you have walked into a cold room, right? There's a cold room in our pilot plant, and actually that is type of air freezing. Basically, we just store the food into the negative 23 something degrees C, and the food will be cooled down by the cold air, and everything is relying on the natural convection. Therefore, it's quite slow. It might take hours if we are putting a large portion, like for example, several cases of beverage there, it will take a long time. Or if we want to freeze the meat product, and say if we move 1 ton, then the inside of meat will take very long time to reach that temperature. Maybe before it's frozen, there's already microbial deterioration occurring. So air freezing is the most basic one, very cheap, very simple design, but sometimes it's just not a very efficient, and may cause some safety issues when doing food production. Okay. So therefore, we always want to speed up the freezing process. So one of the upgrade is called a blast freezer. Okay, so in which we actually pump those cold air at -30 to -45 degrees C with some forced convection. It's like a fan, right? You can see on the image. So very high speed fan. So those fan can actually increase the efficiency of the energy exchange, the heat exchange, so that the food product can be cooled down at a much higher rate. So this is very similar to the dryer, right? Dehydration, which we talked about. So this is one of the blast freezer. Let's watch video. Okay. So you can see the design is very similar. So if you look at this image, you probably find that all the air is kind of directed in one direction, right? So for the cold room, actually the air is driven by natural convection, right? So it's kind of slow process. And here we kind of force the air to flow in one direction, so the air kind of pass through the food product more efficiently. So that's the blast freezer, right? So here's a spiral freezer. So think about the blast freezer. Although it's much faster, but it's still a batch process, right? We need to load some food product and start running the freezing process by blowing cold air, and wait a certain amount of time and take it out and load the second batch of samples. So that's the batch process, not requires a lot of labor, right? So spiral freezer is a continuous version of the blast freezer. So basically, there's a spiral that will be rotating, and the air will blow through those layers, and kind of you can continuously load those samples. So here's the one video about the spiral freezer. Skip this part.
Consumption and an updated control panel. The experience in perfecting its unique vertical airflow system. This provides even air distribution across the belt and throughout the entire spiral. The vertical airflow design uses cross-current heat exchange, the most efficient way to transfer heat. This and the increased turbulence created around the products provides the highest possible rate of heat transfer. This higher heat transfer means shorter freezing times and lower dehydration.
So this is how a a spiral freezer looks like. You can assume it's very robust, right? Because the residence time is long, and it's a continuous process. And every single food product is distributed in very small portion relatively on the belt, so they can be very efficiently cooled down within that time, right? It's not a kind of everything like piled together so that the inside is will be cooled down much slower. But here it's like you are spinning like so it's way much more efficient than the blast and the first cold room air freezer.
Hydration.
Right? Okay, so and tunnel freezer is something that you can assume, right? Because we talked about the tunnel dryer. So tunnel freezer is pretty much like a tunnel dryer, yeah, but the only difference is that we replace the hot air by cold air, right? So that's a tunnel freezer. So you can see everything is so similar. And I'm not going to show you a video because it's apparently you know how that will work. Okay, so and the next one is the fluidized bed freezer. Does that sound familiar? So if you guys still recall the fluidized bed dryer, this one is also very similar, right? So basically, because the when we are freezing those small particle foods like a pea, like peas, like strawberry, like sometimes rice kernels, they're small particles, and when we want to expedite their freezing process, we use very strong air to blow them up so they can have a maximal contact area with the surrounding cold medium, right? So in this case, we can cool down the food product in several seconds. So this is something we call it individual quick freezing technology. Okay, so sometimes in abbreviation IQF, but sometimes we use the full name. So it's used to for those small size food product like strawberries, peas. Okay, and let's watch a video. Although I guess you guys have might already know how that works, but still let's watch this. So this is how it works. I'm just going to show you until here. So basically you have very cold air blown from the bottom, and it's not like shaking, right? It's the hot, it's the cold air actually blowing them up, and there's a feeding and there's an outlet, and it is a continuous process, right? So you can assume how fast that a food product will be freezed in this case. Okay. So a few food products that is made by fluidized bed, for example, shrimps, right? Shrimp is one of the perfect product produced by the fluidized bed, because if we don't cool down shrimp very fast, because due to its very high protein content, then it will be deteriorized or it will have some unpleasant flavor in a very short period of time, right? And we also can use it to do cauliflower, broccoli, and the green beans, a lot of other food vegetables. And the carrots looks perfect to be frozen using the fluidized bed, right? We don't need much air flow. It can be easily shaked. And then the berries, right? Berries, especially because berries we don't the size is small, right? It's light, and we don't want it to when we blow it up, we kind of avoid the damage when between when it's transporting, or kind of when we if we want to load the berry into a cold room, those ones on the bottom, they will be pressed so hard, so they'll cause some economic loss. So Fluid Ice Bed can certainly avoid that. Okay. And a plate freezer. So everything we talked about so far, we're using cold air to freeze it. So basically, the cold air is regarded as the medium contacting with food. But here in the plate freezer, we're actually using the food to directly contact with the plate. And the plate is not cooled down by cold air, but we have the refrigerant that is circulating through the plate to cool down those surface. So it's a little bit different since we're cooling down the contacting area. Okay, so let's watch a video about plate freezing from Dr. Paul Singh.
In plate freezers, we use a product with regular geometry. What we mean is that the product is packaged in rectangular shaped packages. This is a requirement of this type of a freezer because the packages are sandwiched between two hollow plates of the freezer. Once the plates make contact with the package, refrigerant is circulated inside those plates to extract heat from the product. Also, mechanical pressure is applied on the plates so that there is good contact between the plate and the product, as we see in this animation. In this type of freezer, because of the excellent contact between the plate and the product, we get high heat transfer coefficients, around 3000 watts per square meter Kelvin. Now the package must be thin, and a typical package thickness is usually less than 70 millimeters or 7 centimeters. If the plates are warped, or if the package has got large air pockets, then one loses the advantage of high rates of heat transfer because of either not a very good contact between the package and the plate, or considerable airspace within the package. Note that in a plate freezer, since we are not using air, we really don't have any dehydration losses that one may get in other freezers where we use air as the cooling medium. So there is no weight loss of the product when it is frozen in a plate freezer. One of the disadvantages of the plate freezers is that it is a batch operation. You load the plate freezer, you start the operation by bringing the plates into contact with the packages, and once the product is frozen, then you remove those packages from the freezer. So one does not get the advantages that one has of a continuous operation with a plate freezer. There have been attempts made to make this process semi-continuous by indexing packages that are loaded or unloaded from a plate freezer. Typical products that are frozen using plate freezers that you often find in the market include fish fillets, fish blocks, pizza, soups, packaged vegetables such as spinach, mustard, broccoli, that we typically find in rectangular shaped packages in a grocery store.
Okay, so let's look at so this is the demonstration of how plate freezer looks like. And here you can see that those food products that can be plate freeze processed is kind of have some regular shape, right? Because assume if we put one single strawberry on the surface of the plate, the cooling is very slow because the contact area between the strawberry and the plate is so minimal, right? Because it has those curvature geometry. But when you think about fish fillets, it can lay down on the plate and maximize their contact area, which is very important for this case, right? Because our air is not that cold. We're solely using the contacting surface area to facilitate the heat exchange. So in this case, the geometry becomes so important, right? Okay. All right, the next one is the immersion freezing. So the immersion freezing is pretty much like what we talked about last week, last class, the cryogenic refrigeration. Okay, so basically we are using either low freezing point liquid or cryogenic liquid to directly contact with food and to cool it down. So some low freezing point liquid that has been used, they are either high concentration of salt solution or sugar solution, right? So this can refer back to the freezing point discussion we kind of started at the beginning of this lecture, when we have some impurities in the liquid, that freezing point goes lower. And in the industry, people actually utilize that kind of feature of those concentrated liquid, and because it doesn't freeze, so we can use very low temperature of those liquid to cool down the food product. Okay, so sometimes for we use it a lot because it's much cheaper than the liquid nitrogen, right? So liquid nitrogen and the liquid carbon dioxide is good when we need to approach much lower temperature. So this is how the setup looks like. Usually we have a belt or conveyor, and on the conveyor there's typically a reservoir or tank of the cryogenic liquid, and once the product is moved through the liquid, it's kind of stay on the belt. Okay, and we try to make sure that they stay on the belt. Otherwise, once they kind of flow on the liquid, it's kind of hard to control their residence time, right? So this is how it works. Okay, and let's watch this video since we still have time.
Immersion freezers provide a direct contact between the product being frozen and the cooling medium. A typical immersion freezer is a tank that contains the freezing medium, which could be a solution of salt or sugar or alcohol in water. A salt solution, which is also commonly called brine, is commonly used in freezing tuna on ships at sea. These types of freezers are most suited for irregular shaped products such as fish or whole chicken, as one can get good heat transfer between the product and the freezing medium. Due to the direct contact between the freezing medium and the product, one achieves rapid freezing, and convective heat transfer coefficients around 500 watts per square meter Kelvin are obtained in these types of systems. Another example of the use of this type of system is for what is called crust freezing, which is done for poultry to obtain a light colored product. So for this purpose, a crust or the outer layer of chicken is frozen in a brine tank, and later it is finished frozen in a blast freezer. One can also use glycol or propylene glycol solution. However, in that case, the product must be packaged in impermeable packaging material so that it is well protected. At the end of the freezing process, the immersion medium is then washed off the package.
Okay. So that's the immersion freezer. So Dr. Pausing always like to talk about the heat transfer coefficient, right? So you guys don't have to remember what the exact number is. Actually, we'll cover how to do the heat transfer coefficient calculation in 330 and the 440. So you don't have to worry about that. But just give you a kind of a peek of how rough idea how fast it's which one is more efficient in terms of heat transfer. Okay. So the impact of freezing on microorganism, actually freezing will not kill any microorganism. If you see a decrease of microorganism, it's not directly killed, but it's more due to natural reasons. But when the frozen food is stored, actually when the food is frozen, the microorganisms, they are not killed, but their growth is inhibited. But once the frozen food is stored, those microorganisms can grow in typically much higher rate. So it's more like, I guess the reason is because the freezing kind of damaged the original cell structure. For example, in plant, we have some cell wall that kind of support the structure and protect the nutrients from leaking out. But once we freeze it, the cell wall gets disrupted to a certain degree. So the bacteria and the microorganisms get more access to those nutrients. So they kind of grow in a much faster rate once it's stored. So when you're storing a meat product, something like that, please make sure that you consume it rather quickly. Otherwise, there'll be some safety issues. Okay. So frozen food may become health risk if improperly prepared. So that's the microbiology part. And other than that, we have seen a lot of quality change during the freezing. For example, if we have emulsion, right? Emulsion, you guys probably haven't started learning about that. So emulsion is the oil or water. They kind of mix with each other by using emulsifier. So for example, milk is one of the emulsion, and freezing actually can cause the destabilization of the emulsion. For example, if we freeze milk, then maybe because milk has fat, right? In the homogenization, we kind of break those fat into small globules so that they can disperse well in water. But after freezing, those fat can go through a phase separation and flow to top, which will cause the quality to decline. And also slow freezing. Slow freezing will lead to texture change because larger ice crystal will form in a slower freezing process, right? So when we have a crystallization process goes very slow, then the nucleation kind of, there will be very few nuclei, and the ice tend to grow in a much larger size. So I don't know if you guys have heard about those single crystal material growth. That's everything is based on very well controlled crystallization process. They want to grow a large crystal, but single crystal of material, like for special purposes, like airplanes. So in those processes are very slow. But in our case, we want the freezing to be fast as possible. In that case, our ice crystal is small enough to cause the textural damage, right? If you think about the ice cream, if you chew any, if you can feel any big ice crystals, it probably is not that smooth anymore, right? So that's why that slow freezing is not good. And also we'll experience some volume expansion, right, as it's larger than water, and the loss of gases because the volume expansion, those gas originally in the structure will be expelled. So those are the quality difference. And that's why we have a lot of some recommendations for the freezing process. For example, first, we always want a fast freezing rate, right? To inhibit the growth of large crystals. And second, we want to make sure the core, the inside core, can be frozen to -18 degrees C because the surface always cooled first. Cold is always cooled down first. But what if the size of food product is very huge? Then the heat transfer becomes slow. Then we have to monitor the temperature at the cold point. Actually, in this case, will be the hot point, right? And the third one is that we have to minimize the temperature fluctuation. So one example I always want to discuss with you guys is what if our refrigerator is not very stable, the temperature kind of fluctuates from -10 degrees C to -18 degrees C. Is that good or bad? Because of the time limit, I'm just going to directly tell you why it's bad, because we know that a lot of food products, they have different freezing point, right? Some freezing point is close to 0, some can be lower. So if the temperature fluctuates, although it looks like it's below the freezing point, but for some food product or at certain region of the food product, because the food is not a homogeneous product, so at certain region, this temperature difference might already triggered a thaw and a freezing cycle. So in that case, we're actually kind of going through the cycle to continuously cause the textural damage to the food. And also the ice crystal might tend to grow in this case in larger sites. So that's a reason that we always want to minimize the temperature fluctuation in a frozen food. Okay, and finally, because during the freezing process, the product volume will expand due to the ice formation. So we have to make sure that our package will not break. So that's all the recommendations. And I was planning to do a breakout room for you guys to discuss what. So we always talk about the faster freezing rate is better, but since we are running out of time, so the reason, so there are some factors that can potentially impact the freezing rate. First is the refrigerant temperature. And the second is how fast it circulates, right? Because the better the circulation, then the more cooling efficient, right? And third, we want to have a good heat capacity of the refrigerant, which means 1 kilogram of the, for example, liquid nitrogen can only bring down maybe 5 degrees C of the water, liquid water, but if we use 1 kilogram of liquid carbon dioxide, that might help to bring down 15 degrees C of the water temperature. So that's why we always want high heat capacity of the refrigerant, right? And the thickness for food, we also want thinner food, right? So the cooling process is more homogeneous throughout the food. And then finally, a good thermal conductivity of the packaging material, right? Because think about the plate freezing, right? It's the direct contacting between the low temperature plate and the packaging material. So in that case, if the heat exchange is more efficient using a high thermal conductivity packaging material, then we can cool down the food product more efficiently. All right. Any questions here? It's a little bit fast because we kind of went through a lot of announcement at the beginning. So, any questions about this part? Okay. Okay, good. Did I miss anything in the chat box? No. Okay, cool. So a little bit summary, wrap up. So first we talk about the definition of purpose where we're doing freezing, right? And then the freezing point, it's always lower than the 0 degree C. And what is the supercooling, right? And how to calculate how much energy will be removed during freezing process. And also we went through different freezing systems, and you guys can see it's so similar to the drying system, right? And finally, we kind of learn about the quality in the impact of freezing on quality. So that's it for today. If you have questions, you can stay online. If not, then I'll see you guys next week. Don't forget about the assignments and the lab report and the quiz that is due tonight, okay?
Thank you. Bye.
you.
Thank you.
Bye. Thank you.
Thank you.